Okay, so far we know a couple of electrical engineering components, including resistors, dependent source, independent source, and of course wires. Now we are going to learn about a new one today, which is an inductor. Now, if you've taken Physics 202, I think you must be familiar with the idea of inductance. If not, it's fine. But we have different types of inductors. Two of the most popular ones are solenoidal and toroidal. And generally, any actually conductive wire that is that you have it as winding around some sort of core, it can act as an inductor. If you look at this hand-drawn figure, you see that there are currents passing through the wires around some sort of core, which can be anything, any insulator material, and that current will create some sort of magnetic flux to pass through the core, and it will create some voltage across this element. Now, this is the fundamental definition of inductance. As you know it, it's phi or phi in units of Weber divided by current in amps. So that is the main definition of inductance. We're not going to talk in depth about the physical aspects of inductors. We mostly want to consider them as a circuit element and apply them in our circuits. So the first definition of inductance is the ratio of magnetic flux, phi, to the current I. Now, this is the circuit symbol that represents inductance, and the element that has this property is called an inductor, okay? And shown with the letter L. Now, probably a more important definition of inductance, which is more important in electrical engineering, is how inductance behave in a circuit. Now, let me read this for you. Inductance is a measure of how an element responds to a changing magnetic field or a changing current. Now, if you remember resistors or resistance responds to current, okay? If you have a current and you have some element resistance, it will create a voltage, right? So resistance responds to current. But an inductance or inductor responds to a change in current. That's a very important difference between these two. So if you have a current, the inductance won't respond to it. Only it will respond to it if there is a change in a current. And that's the fundamental idea behind defining the main equation that governs the behavior of inductors. Now, we already talked about this equation, phi is equal to Li, in the previous page. How about the second equation? You must have seen it somewhere. I'm not sure, high school or in Physics 202. Can anyone remember what was the name of this equation? What was the guy's name that actually came up with this equation? No. Faraday. Have you ever heard of him? That is the Faraday's equation, okay? Now, if you combine these two equations, look at the second one, V is equal to d phi over dt. Instead of phi, substitute Li, and you will get this equation. So I want you to focus on this equation. This is the main and fundamental equation for inductors. And compare it with the highlighted part, okay? Are they consistent? So voltage is created when there's a change in current. Is that consistent with that highlighted part? Yes, because inductance is the response or is a measure of how an element responds to changing current. Current is, for our purposes, is proportional or not directly, but is related to magnetic field. So this is the main equation that we are going to deal with. Remember, this equation is valid if the current that you're considering is entering from the positive terminal of the voltage, exactly like we had it for Ohm's law. What if the current enters from the negative terminal? What happens to that equation or formula? Just add a negative sign, okay? You should apply a negative sign there. Now, what is the units of L? What is the unit of L in our equations? So, before talking about the SI units, let's write whatever equation that I know about L. So, the first one from the first page. L is equal to phi over I, right? From the box equation, what is L equal to? V over di over dt. So I can write it as V dt over di. Do you agree with that? In terms of units, so what is phi over I? Weber per amps, right? So that's 1 unit for inductance. Or from the right-hand side of this V dt over di, what's the unit associated with that? What's the units of V? Volts. What's the units of dt? Second. What's the units of di? Amps. Remember, I and di have the same units, right? Okay, now, do you know what we call these in SI? You know what SI is, right? Okay, so what is the SI units that it's most commonly used for inductors? Have you heard of that? Henry, or Henry, or Henry, because that's a French word. He was a French scientist, so don't be surprised if I use Henry sometimes. So that is equivalent to H, which is Henry. Okay? So now that we have introduced the concept of inductance and the associated element, which is inductor, let's compare an inductor with a resistor. Left circuit. Give me the relationship between V1, V2, I, and R. Yes?
You calculate the current by doing V1 minus V2 over R.
Perfect. So do you agree with that? V1 minus V2 is equal to Ri. What is that called? Ohm's law. Now, can I write this for inductor? Similar to this? Absolutely not. You calling it Ohm's law. What does Ohm means? Resistor. Is that a resistor? No. So what's the equation relating V1, V2, L, and I? Do you want to peek? Perfect. V1 minus V2 is equal to L di over dt.
dt being time.
dt is the differential in time. Yeah. So this is very important not to confuse inductors and resistors, okay? They have different governing equations. Let's find VL in this simple circuit. So, first of all, can you tell me what is this current? 2 amps. So, let me actually write it like that. Let me write it as IL is equal to 2 amps. Now, VL is equal to, what's the equation for the inductor? L DIL over dt. The L is 2 millihenry. D over dt of 2. It's equal to? What's the answer? 0. What does it mean? What's the definition of inductance? It responds to a change in current. The current is not changing, it's fixed 2 amps. So there is no voltage across the inductor. So inductor is behaving like a wire, a short circuit. There's no voltage across it, okay? Super important. In DC circuits, inductors behave as short circuits. Now, do any of you know what DC stands for? Direct current. For historical reason, it's called DC. It stands for direct current, but it doesn't necessarily is limited to, it's not necessarily limited to direct current circuit. Any circuit that has everything in it as a form of independent sources is called a DC circuit. For example, if you have a voltage source that is independent of time, it's also called a DC source, okay? I know that DC stands for direct current, but it applies to anything that is time independent, okay? Let's find voltage for a piece of circuit, which is shown here, an inductor. The voltage across it is, we want to find it, and the current is given to you in a plot. So, okay, let's write the equation. V is equal to L di over dt. What is the value of L? 1 Henry di over dt. So it's equal to di over dt. The information that we have about I is in the plot. Now, what is the equivalent of time derivative or derivative when you have the plot? Slope, right? So we're going to deal with this plot in piecewise, right? Because it has different slopes in different regions. So let's see. T between 0 and 1. di over dt is equal to a slope. What is the slope here? 5 minus 0 divided by 1 minus 0, and it's equal to 5. Can someone tell me what is the units of the slope? Amps per second. Is it volts? No. It lacks something to become volts. The Henry, right? So remember, if you're talking about the slope unit is amps per second. But since your Henry value is just 1, it can also be equal to 5 volts, okay? Because just multiplied by 1, yeah.
So can a Henry be wrote as an ohm second, or is that just not necessary?
Ohm second, I have to check how you got that.
So voltage is like doing Ohm's law is
Yes.
IR.
Yes, yes. Oh, yeah. That's actually,
And this is a Henry times the amps, like you're saying.
that's ohm seconds.
But are
Yeah.
they not like actually related?
How do you want to relate it? In your third part of the course, for the third exam, you will see some relationship between them. But until then, no. Okay? Yeah. But that's a very good observation, actually. Okay. Then t between 1 and 3, di over dt is equal to slope, and it's equal to 5 minus 5 divided by 3 minus 1, and it's equal to 0. T between 3 and 4, di over dt is equal to a slope, and it's equal to 0 minus 5 divided by 4 minus 3, and it's equal to negative 5 amps per second. Any problem? Okay, let's plot this. So I have 1, 2, 3, and 4. Between 0 and 1 is 5 volts, and between 1 and 3 is 0, and here is negative 5 volts. Any problem? No? Okay, before talking about this example, let's consider this part. So if current is given to you, how do you find the voltage? LdI over dt. Current is given, voltage is asked. Now, what if voltage is given to you and they ask you to find the current? What is the opposite of taking the derivative? Integration. But you remember, from anything that is related to integration, if you are solving an integral equation, you need the initial value, right? So if you want to do it that way, you need the initial current to find the current, okay? So this is the equation. I mean, we've done it like several times in this course, finding the opposite equation of a derivative, which is an integration. So I don't need to go through that derivation of the formula, but I don't like to throw formulas at you without proof. So if you're interested, the proof is brought here. Pay attention to the formula, that's very important. That gives you the current of an inductor when the voltage is given to you, with one extra piece of information, and that is your initial current. This is actually the foundation that shows you that inductors have memory, or inductors can store magnetic energy. How can I say this? Think of this case. If the voltage across an inductor is 0, the integral goes to 0, right? But still you could have some current in it. So it kind of works like this. If you have problem understanding the concept, wait until 2 more lectures and we will talk in more detail about this. But it's like this. If you connect a current to some inductor, okay? And then detach the inductor from the source, it will hold the current in itself, okay? So it has memory, it can store energy. The two elements that we are going to learn in this lecture and next lecture, inductors and capacitors, have the ability to store, okay? So we're starting with inductors. We're not going to spend a lot of time about how they're going to actually store energy. We're mostly interested in their circuit behavior in these two lectures, but we're going to talk some details about them in not the one after that, when we talk about transient analysis.
Is that part of how batteries are made?
Pardon me?
Is that part of how batteries are made?
Yeah, capacitors, yeah, especially. Not all of them, but yeah, some. Okay, so this is the equation, the backward equation. But I want you to remember this for your conceptual question of the second exam. Inductors store magnetic energy, not electric energy, okay? Because they are associated with magnetic flux passing through them, okay? You will see later that capacitors are associated with electrical energy, or because they store charge, okay? They store charge. So I want you to see and understand the difference. Okay, let's do this example based on the integral equation. Now, in this example, voltage is given to you, and they are asking to find the current. Remember, the one extra piece of information should be provided if you want to find the current, and that is the initial current. So let me write the equation. IT is equal to 1 over L, the integral from T naught to T, Vt prime dt prime plus I T naught. Now, let's simplify this. The value of L is 1, so 1 over 1. What should I consider as my T naught? Sorry? 0 second. So 0 to T. Or let's actually do it, let's write it like that. Let's, for now, write it as T naught. And now, how do you approach this problem if you want to integrate? Piecewise, right?
Area under the curve.
Yes, area under the curve is correct if you want to
Get a value.
let me rephrase what I said. Area under the curve is always correct, but there are some cases that you can't do it, right? If it is a curve, you cannot calculate the area. Actually, the guy that, I don't know, a couple of thousand years ago came up with integral faced the same issue, right? They wanted to calculate the area under a curve, and they couldn't use geometric equations. That's why they came up with integral. Integral was created as a way of calculating the area under the curve. So let's do it piecewise and see where we can go from there. So t between 0 and 1, my equation changed to it equal to. What should I consider as t naught? 0. 0 to t. What's the voltage in this interval? 5. And what is I T naught? 0. So your integral becomes 5t prime from 0 to t, which is equal to 5t. Okay? Let's go to the next interval, t between 1 and 3. So it is equal to integral. What is the initial value? What is the initial time? 1. Remember, the last value of the previous interval is the initial value of the next interval. So what is the voltage in this range, in this interval? 0. And what is the initial current for this specific interval? So there's something missing with my calculation of the previous interval, right? Whenever you find the function of each interval, take an extra step and find the value at the end of that interval. Why? Because the end of each interval is the start of the next interval. So I'm going to write it like that. I at 1 second is equal to 5 amps. Now I'm going to use that 5 amps with my next interval. Am I making sense to everyone? Plus 5 is equal to, the integral is 0 because the integrand is 0, so that is equal to 5 amps. Any problem so far?
Would that be less than or equal to, or still just less?
Pardon me?
Would that less than sign still be just less than, or could it be a less than?
Are you talking about which interval?
The 1 through 3.
1 through 3. Okay. So the current is equal to 5 amp. It's fixed. It's not changing in that interval. Okay? So did I answer your question or still? Okay? If you're talking about specific points, for example, at t equals 3, was that your question?
Yes.
You're familiar, this is a math concept. You're familiar with the concept of continuous function, right? Right? So it's not like we can say what's the value of voltage at exactly t equals 1 second. What we can say is like that. What is the value of voltage right before 1 second and right after 1 second? Because the function is not continuous. Okay? T between 3 and 4. It is equal to, what are the bounds of integral? From 3 to t. And what is the function in this range? -5. And what is the initial value at t equals 3? Five, right? It's equal to -5 t prime from 3 to t plus 5, which is equal to -5t plus 5. Let's calculate the value at 4. What is I of 4? Did I mess up something? Yes, I did.
Because it's a.
Yeah. So -5t plus 15 plus 5 plus 20. So what is I of 4? 0 amps. Okay? Now, let me add a second option for you. You've seen this before. I've talked about this, but since math is not your favorite topic, sometimes you forget it. So instead of dealing with the whole integration and finding the full function, this is another option that you have. So instead of writing IT for the first interval, I can write I1, meaning that I only want to find the last point of that interval. How does it change the integration? 0 to 1, 5 dt prime plus 0, and it's equal to 5t prime from 0 to 1, and it's equal to 5 amps. Most of you prefer the purple ones. And you can do it for the next one. You can write I of 3 is equal to integral from 1 to 3 of 0 dt prime plus 5, and it's equal to 5 amps. For the third one, you can write I of 4 is equal to integral from 3 to 4 negative 5 dt prime plus 5. It's equal to negative 5 times 4 minus 3 plus 5. Did I do it right? Yes, equal to 0. Which one do you prefer? The black ones or the purple ones? Is there any limit to using the purple ones? Okay, so let's use the purple ones. What is the current at 0 second? You have it as 0. 1, 2, 3, and 4. What is the current at 1 second? 5 amps. What is the current at 3 seconds? 5. And what is the current at 4 seconds? So these are the points, right? Okay, so is this your plot? How do you connect them? Why?
That's what we decide.
And I decide to fail you. Why did you decide to connect them using a straight line, not like this?
Have to go back and divide by, what's it called, the L to get the slopes.
Yeah. See, look at the voltage. The voltage has constant values in each interval. So what is the integral of constant? Line. First order line. If this was something other than constant values, then the purple method won't answer, won't work. Am I making sense to everyone? If you use the purple ones, it's only applicable if you know that the final connectings are going to be first order lines, okay? Otherwise, it would give you some problems. But if you look at the black ones, you see that you have the functions. See, the first one is 5t, just an increasing with a positive slope line. Second one is constant, 5a. And the third one is negative 5t plus 20 with a negative slope line, okay? So most of the time the purple ones work, but if there are curves involved, then they probably won't, okay? Was there any other way of doing it except these two? Yeah, you could use just the area under the curve, right? What's the area for first part?
From 0 to 1, 1 times
I1 is equal to the two sides, 5 and 1, right? For 3, from 0 to 3, if you want to calculate the part from 0 to 3, you have to include two parts. The area under the first interval, which is 5, plus the area, which is 0. Again, it's going to give you the same value. So area is equal to 0 plus 5 amps, and it's equal to 5 amps. How about the value at 4? How do you calculate the area there? You have 3 intervals, remember. The first one gives you 5, the second one gives you 0, the third one gives you -5 because it's below the horizontal line. Okay? But the purple one and the green one only works for very well-defined shapes. Otherwise, you have to do integration. Okay. If you don't want to copy anything here, let me move to the next example. So a current curve is given to you, not curve, a current plot is given to you, and you're supposed to find the voltage. Okay, let's write the equation. What is the equation? L di over dt. L is 1 Henry, so it's going to be di over dt. Right? Let's calculate them. Okay, so what is the voltage between 0 and 1? What's the slope between 0 and 1? 0. What's the slope between 1 and 2? 0. What's the slope between or greater than 2? Again, 0, right? So is that acceptable for my plot? What's wrong with that?
Well, there is a current change.
Yeah, that's a very actually good point. I wasn't thinking of that. There is current change. How come the voltage is not responding to that? Because that's the fundamental definition of inductor. It responds to change in current. There is change in current, but how come the voltage stays at 0? So,
There's no time change. It's like a change. It's the volt or current change over 0. It's undefined.
so
Well, I feel like that's accurate. I just feel like there's something more going on.
yeah, what is that extra things that's going on? So let me ask you this. So you associate the horizontal line, the green lines, with 0 slope. How do you, or what do you associate the vertical lines in terms of slope?
Undefined.
If you don't want to be very strict about math and be in engineering for a moment.
Instantaneous change.
It's a
That's
really-
not an engineer.
It's a really high. It's a really high slope.
It's a really high slope, right? Just think of it in layman terms, okay? If you're running on a flat surface, the slope is 0. But what if you're trying to walk over a vertical wall? The slope is very high, right? Drive a car or even walk. So it's very close to infinite, right? If that is exactly vertical, do you agree that slope is actually infinite? So if I want to make this expression correct, I should write it like that. What about t equals 2? Negative infinity. So that plot is not complete. This is 1, this is 2. This is how I represent it. This is a very important function in engineering and physics. It's called delta Dirac function, which goes to infinity in 0 seconds. You might not actually get involved with it if you are from a major other than electrical engineering or physics, but this is a super important concept in both of those majors. So, okay, is there anything wrong here? Everything so far mathematically is justified. Now, I have some current passing through my inductor, and this is my voltage. Is there anything wrong? Sorry?
It's not, the number 2 and 4 not being taken out when there's clearly a change in current. And when we know it is changing, you have to set how much it is changing.
If you want to be very strict about math, you're correct. But we are considering, okay, let's do this. Let's consider that slope not being vertical, but being very, very, very sharp slope, okay? So this is not considered infinite, but this is a very huge value, okay? But my problem is not that. My problem is that, let me see what you have to say.
I was gonna say it just seems really dangerous.
How come?
Like there's a huge voltage spike that could destroy stuff. It could hurt something.
Well, that's not actually dangerous. That's science fiction.
Oh, is it current that hurts?
No, the problem is that you have limited amount of currents, right? 2 amps and 4 amps. And you have 1 Henry of inductor. How come you can get infinite voltage? That's very good.
Our relatives, we have a very distant relative point.
Sorry?
So we can set the relative point. We have it set very far away.
No.
So
The thing is, that current is completely reasonable. That value of the inductor is perfectly reasonable. How come you can get infinite voltage across something?
would it be something that's like that induces an increase in current that's not a current source? Or is that what
I don't care where it is coming from. This is more like a Marvel movie. You have some limited current applied to some very reasonable component, and you're getting infinite voltage.
we're doing something wrong?
What's wrong with that?
I mean, nothing's wrong with it logically.
Let's do this and find out.
It just seems like that's not realistic to just change current and
So let's assume that this is your current source pushing the value of the green function to some inductor. Now, and your inductor is 1 Henry, and this is the voltage. First of all, how can you realize that green function? Let me make it a little bit easier for you. Let me do it like that. Because it's not going to be different. So let me make it a little easier. everything else is still the same, right? I just changed the values from 2 and 4 to 0 and 2. Everything else is exactly the same. Now, this is my question. First of all, how can you realize the green function, the current function?
The current source. Wait, so the current.
Imagine the current is 2 amps. How can you make it go suddenly equal to 0?
Short circuit. Or open circuit.
Just very fast, you have to react very fast. Just remove it instantly from the circuit. Okay? That way the current source goes to 0, right? But here is the thing. Do you remember I told you that inductors store energy? Store current in them? So as soon as you unplug the current source from that circuit, this is what happens. The current that passing through the inductor won't change abruptly. It will go slowly down to 0. Why? Because otherwise it will create a huge amount of voltage across it. So if you're interested in knowing more about this, we will talk about this in 2 lectures from now. But right now, understand this. If you, by any means, disconnect the current source from this guy, the current that's passing through the inductor won't drop to 0 instantly. It takes time. It is delayed. And this is the conclusion of that, a very important concept for your second exam. The current flowing through an inductor cannot change abruptly. Never.
What about when you're adding the current back? Is that initial jump from 0 to 2, that's also not possible?
Also not possible.
Originally
Yeah.
connected.
Always think of it like that. If you have a current of an inductor at 2 amps, for example, okay? And the current of the current source dropped to 0 instantly, the current of the inductor will act like this. Imagine this is 2 amps.
I mean, like,
Slowly.
Is that 0, and then
Okay, let's do it the other way.
would just be the opposite.
You're going from 2 to 4, right? So imagine that this is your current source. This is how your inductor responds to it.
So quick, but not immediately.
No, there's nothing immediate in inductors or capacitors, as you will see next lecture. Okay, so they store and they have delay. Okay, but this is something that we talk about in the next, not the next one, the one after that. Okay, what I want you to understand for now is this. There's no way that the current passing through an inductor changes abruptly. However you want to force it, the inductor responds in time, delayed. Okay, let's do an example. Vt is given to you, some function. It, you're supposed to find It, and the value of the inductor is also given to you. So what should I do? So first of all, can you tell me what's the voltage across the inductor? Do you agree that these are parallel, so Vt is dropped across the inductor? So what is the equation governing the behavior of inductor? Right? This is the integral equation. I'm trying to find current based on voltage. Okay? So your inductor is 1 over 50 millihenry. The integral, what should I consider as my lower bound? 0, because 0 is given to you. To t. What is Vt? It's given to you, the function. 5e to the negative 20t prime. dt prime. What is the initial value? 1 amps. So if you don't know this, what is e to the power of at integral? 1 over a e to the power of at. What is 1 over 50 milli? It's like 1,000 over 50, which is 20. So I'm going to write 20 here. Then 5 comes out of the integral. And the integral of e to the negative 20, what is it? 1 over negative 20. E to the power of negative 20 t prime from 0 to t plus 1. It's equal to the 20 and 20 cancel out, negative 5 plug t, give you e to the negative 20t, plug 0 to exponential. What will it give you? 1 plus 1. It's equal to negative 5 e to the negative 20t plus 5 plus 1, which is plus 6 amps. Okay? Any problem with this? It's basically a math question, right? Okay. Now, do you remember the fundamental equation of, were you writing, Cage? Do you want me to scroll up? Okay. Okay, what was the fundamental equation for energy?
T equals VI. Or energy.
Okay, what was the fundamental equation for power?
T equals VI.
That's not the most fundamental ones. Okay, the rates of change of energy, the time rate of change of energy. But what was the most useful equation for power? It was VI, right? So still, I mean, can we apply the same equation for inductors? Yes, we never said anything about being a resistor. We can apply this to any electrical element. VI, it's your power. The only thing that is changed here is the time dependency, right? Now, do you agree that instead of V, I can write LdI over dt? And instead of I'm just going to write II. Okay? So that's the equation for power. So nothing new, actually. It's not something worth memorizing. It's just replacing V by the equation and I is I. Okay? But as you mentioned, the fundamental definition of power was rate of change of energy, time rate of change of energy. So if you're given P, how do you calculate work or energy? Take the integral over the interval. Let me ask you a question that you can actually feel it with your bones if you are not living in your parents' house. So let's say that you're keeping a light on, okay, for 12 hours. And someone else is keeping that light on for 10 hours, the same light. So the number that is written on the lamp, on the light bulb, is usually like 20 watts or something. It's the power, right? How come one of you is paying more for the bill, for the electricity bill?
The time.
Because you're paying for energy. And what is energy? Power multiplied, or the fancy term for multiplication is integration. Power multiplied by time. That's why you should pay more. Now, so you agree with this equation. Energy is just the integral of power over time. I don't need to go through the proof. The final answer, the final result is that energy of an inductor, energy absorbed by an inductor, is 1/2 Li squared. This is a very not super important. You won't get a lot of question in it about it, but usually it's a source of confusion for students because they memorize this equation, but somehow they relate it to power. This equation is not about power. It's the energy, okay? I want you to remember that. Memorize this. This won't be given to you, but this is the energy absorbed by an inductor. How do you handle power of an inductor? Exactly as before, VI. If you have V and I, you can find the power. The formula that you're memorizing is for energy. This is the third time I said it in less than 2 minutes, okay? Remember that. Okay, now what happens if I have multiple inductors in my circuit? They can be either series or in parallels. Can I combine them? Yes, the proof is brought here for you. It's very easy, straightforward. But the good news is that inductors behave exactly the same way as resistors when they are being combined. If they are in series, just add them together. If they are in parallel, do your thing, whatever, inverse them, add them, and then inverse again. Okay? So they are treated exactly the same way as resistors. Just so you know, or you're following what it means, give me the equivalent inductance or inductor of this circuit. I don't need the value, just tell me what to write. Where do you start from? The right. So do you agree with 20 plus 12 plus 10? And then parallel with 7. And then plus 4 plus 8. Okay? That's the equivalent inductors. Any problem? Okay, let's find V in T in this circuit. IS is given to you, and we want to find V in. So I'm looking for suggestions. Let me ask you this. Can I apply Ohm's law to inductors? No, definitely not. What other rules or laws of electrical engineering you know from your first exam? KCL and KVL. Can KCL and KVL be applied to circuits including inductors? Both of them, yes or no? KVL and KCL. If you remember our review meeting, what are KVL and KCL based on from physics? Conservation of energy and charge. Can they be violated under any circumstances? No. So it doesn't matter whatever you have. If you have a resistor, a capacitor, inductors, and me in the circuit, you can still use KCL and KVL, right? So, knowing that, Answer my question. How do you approach this problem?
Replace the inductor with the while, right?
Why?
Because that would behave like whenever the current source is applied to it.
Is the current source constant?
No.
Is it?
No, it's changing time.
It's changing with time. Are you allowed to replace the inductor with a piece of wire?
You could do a,
Let me bring that. There's a very important word in this, and you missed that. What is that word? DC circuit. Is that a DC circuit? No.
and it's in there to reach the current source. Or induce the current.
So here, it's not a DC circuit. Is it obvious for everyone? DC means there is no time dependency. You're clearly seeing that T. So you cannot replace the inductor with a wire. Okay, what should I do here? Yes.
You could do the voltage drop of the 10 ohm and then like do so that would just be I times that and then
Yes.
we're gonna have our time variable or time what's it called? Our time period.
You don't need to. You're supposed to find a function. You don't need to find.
Oh then yeah, you can just multiply.
So do you agree that if I multiply 10 ohm by that value 2.6 T squared, it will give you the voltage across the resistor?
Yes.
What kind of magical equation did he use? Ohm's law. It doesn't matter if the current is time dependent or independent or whatever. Just multiply resistor by current, it will give you voltage. How about the inductor?
That would be the other equation.
LdI over dt, right? So let me do this. Let me call this guy VR and this guy VL. Now, can you find VR easily? Let me do this if it's still bothering you. What is the current, the red current? IS. What is this current? IS. So let me ask you again. Can you find VR easily? Multiply 10 by IS. Can you find VL? It's 5 di over dt, dis over dt. How do you find V in? Write a KVL around the loop, right? What is VR? 10 times IS. What is VL? 5 times dis over dt. It's equal to IS is 2.6 T squared plus 5 d over dt 2.6 T squared. 26 T squared plus. What's the derivative of 2.6 T squared? Is 5.2 T. It's equal to 26 T squared plus 26 T. What's the point of this example? That you know you can use KVL around any loops, whether it has inductors or not. and the units is in V.
So in this case, voltage is increasing quite rapidly.
Yeah, voltage is increasing with time. Yes. Yes, yeah, because T is positive, yeah. So it's current. The current source is also increasing. Okay. Next example. How do you approach this?
Parallels, they have the same voltage drop,
So
or is that not?
the resistors, you tell me.
So, I believe, and I don't know if we learned in electrical, they were in series and it works. I'm assuming they have the same voltage drop in parallel.
When I was talking about parallel definition, did I limit that to resistors? Or I just use blocks, if you remember?
The elements.
The elements. So can you say that the 510 ohms are in parallel? Yes. Because they share both terminals, right? So this question is asking you to find I. How do you find that?
You have to find.
Someone said it. KCL. Okay? So let me do this. Let's call this current IR. What is KCL? Tell me KCL. At the top node.
VS minus almost at the bottom one.
Let's start from left.
Oh,
Okay, let me do everything exactly as before.
it'd be negative.
I'm guessing you were waiting for this.
Well, yeah. Thought we had to clarify.
What do you call the red? How do you label the red node? VS. So write the KCL. From left. Why do you jump over that? You leaving that for the next person? It's exam. You're the only person.
Negative VS.
KCL, you're dealing with V. What's the thing that you need to find?
We need ions.
Okay, include that in your equation. Why are you escaping from it? Do you agree? IT is equal to. What's the current in the middle branch? VS minus 0 over 10 ohms. Plus, what's the other current? VS minus 0 over 500, right? Don't nod.
No, because it's L.
It's not a resistor.
It's the integral.
Don't apply Ohm's law. Yeah, I heard you said no. What should I write? No.
It's 1 over, it's
1 over 5
integral.
integral
Yeah.
from 0 to t. What's inside the integral? Vs minus 0, right? I'm emphasizing that minus 0 because so you know if the other terminal is not 0, you have to include that. Plus 4 amps. Anyone having a problem with this? It's not a new concept, it's just KCL. So what is Vs over 10? 2.1 t plus 1 over 5. Integral from 0 to t of 21 t prime dt prime plus 4. It's equal to 2.1 t plus 1 5 21 over 2 t prime squared from 0 to t plus 4, and it's equal to 2.1 t plus 21 over 10, again 2.1 t prime, no, not t prime, t squared and plus 4. Sorry? It's not critical. Yes, you can find. I mean, you just have to. Let me see if there is actually one. No, there isn't.
Derivative 0. It's always 0.
It will be a complex number. It won't give you a real root. So there isn't any point that gives 0. And even if there is, I mean, it doesn't have like a special value for us. Okay. Any question? You can start your in-class assignment.